Thank you very much to all the organizers for inviting me to this very, very interesting meeting. I learned a lot. I'm actually surprised to be invited to this meeting because everybody knows, Stefan knows that my favorite atomic system is dysprosium, and that it's not a simple system. But anyway, today I would like to talk about some of the elephants in the room. Let's see. First problem. Yes. I would say if you think about it, it's really not an obvious thing that we can even have a conference where for the whole week we are discussing the discrepancy between experiment and theory in the 5th digits, 10th digits, 12th digits, and why it is not obvious that it can even be like that is because there is an elephant in the room. Physics is in a big state of problem because we have evidence that most of the matter in the universe is the so-called dark matter, and what it is we don't know. So how can this coexist with precision physics is not trivial. In fact, there are many elephants if you think about it. We, for instance, do not really understand at all why in the universe we mostly have matter and very, very little antimatter. There are some rather contrived schemes how this can happen, but they involve violations that we have never seen, baryon number violations, and so on and so forth. So we really don't know. There is another, maybe a slightly smaller elephant in the room, which is that I said that there is 5 times more dark matter than normal matter, but why is not 50 million times or any other number? Why is that approximately we have the same, roughly, on the logarithmic scale amount of matter and antimatter? Needs to be explained, perhaps. Then the theory of strong interactions, quantum chromodynamics, it admits very easily violation of CP, and we don't see it. People measure EDMs, and they are still 0. It needs to be explained. There is also a hierarchy problem that the scales, like the masses of the particles, even the heaviest ones, which are hundreds of GeV or something like this, are so many orders of magnitude smaller than the natural scales of physics, the grand unification scale, the Planck scale. There's just 10 to the 16, 10 to the 19 G. Why there's such a huge gap there? We won't even touch dark energy. And all of these problems unexplained. There is one sort of intellectually appealing possibility. I would say there is no deep motivation for it, but I think it's appealing to think that maybe all of these things, or at least some of these things, are actually one and the same elephant, and we're just seeing different manifestations of the same elephant. And to me, the more elephants are explained by one and the same thing, the more appealing this scheme is. But it's a kind of aesthetic argument, I would say. Anyway, back to dark matter. What can it be? And I must say, whenever we are talking about something that nobody has seen, emotions go high and people really are sure. It's like a bit like with religion, you know, people have never seen something, they have strong feelings about it. But with the dark matter, it's a bit like this. And recently, one of the sort of paradigms, which is becoming more and more popular, it used to be like a very much fringe paradigm, and now it's one of the main paradigms in dark matter, is that dark matter can be some kind of an ultralight bosonic field. Now, it is very beautiful and simple to explain why if dark matter consists of one sort of particle and the particles are light, they have to be bosons. When I first learned it a few years ago, it just blew my mind how beautiful it is. Right? So basically from high school physics, you can determine the spin of the particle under some very simple assumption. And the key fact here is that dark matter is associated with galaxies. And galaxies have escape velocity on the order of 10 to minus 3 of the speed of light. So dark matter should be moving slower than the escape velocity, otherwise it will escape the galaxy. And if you put a lot of fermions in the same box, even yeah, then there is a Fermi velocity, and this Fermi velocity has to be smaller than the escape velocity. And so it turns out that if you go below about 10 electron volt or so, it doesn't work anymore. The fermions would escape, so it has to be a boson. And now the underlying field can be pseudoscalar. This is a very popular thing, the axions. So axions are appealing for the elephant reason that they were actually introduced originally to naturally explain the strong CP problem, and now they can also potentially explain the dark matter problem. Now, people say that, okay, maybe these problems are separate, different elephants, and then one can introduce the axion-like particle, which is also a pseudoscalar ultralight field, but it doesn't solve strong CP problem. And then you can go to another intrinsic parity, to a scalar and such particles. Like there are many different dilatons, moduli, whatever. They appear somewhere in the string theory and could also be sort of natural candidates for dark matter. To me, a very exciting and relatively recent possibility is something that's called relaxion, which is a play on words. It's an axion that undergoes relaxation oscillations in the early universe. And there are different kinds of these things, but there is a particular one that I like very much, is the one championed by Gilad Perez at the Weizmann Institute. And the reason I like it is that it has mixed parity, so it has property of both a scalar and a pseudoscalar, and so you can look at it for it with different kinds of detectors, basically atomic clocks and magnetometers. Then there are vector particles, spin one. These are dark photons or hidden photons, for example. Okay, so that's the first paradigm. There is another paradigm, and I think this is a particularly attractive one because all the elephants, except maybe dark energy that I showed on the previous slide, are naturally explained by this paradigm. If you are interested in it, let's talk at coffee, because it's something completely different, as they say. Okay, then we already heard about Milli charge particles. A recent thing that you may or may not have heard about is something that's not even particles. You know, so you sometimes hear the following words that okay, so say dark matter could be some kind of a scalar field, and scalar field mimics variation of fundamental constants, and that's how we look, for instance, for oscillating energies of levels due to this field. Now, if this field exists and forms dark matter, these kind of particles, underlying particles, should also participate in interaction, and it should lead to Fives forces. Virtual particles lead to Fives forces. And this not even particles is basically a real violation, real variation of constants, not mimicked variation. And the consequence of this will be that there are no Fives force manifestations of these particles. So you would see them in dark matter, but not in Fives forces. I think this is a sort of a nascent paradigm, but some people are working on it. Of course, it could be other things, gross misunderstanding of gravity, like the Mon theory, and some other things. Now it's kind of a joke that I put WIMPs last, because for 30 years, this was the dark matter that everybody is still looking for. It's not a bad candidate. It's still possible that it's a WIMP. Okay, by the way, if you are intrigued by this ultralight dark matter business, there will be a Bad Honnef school which is sort of aimed at PhD students and postdocs, and it starts on the last day of July, and it goes for about a week, and it costs, I think, 100 euros for German Physical Society members, and otherwise 200 euros, and everything is included. It's a really good, and even the speakers, you know. So but anyway, it's a very, very good, I think, event to learn about this. So how do you go about trying to understand these elephants? Well, there are direct searches and indirect searches. And for instance, you can, as I'll show a little bit later, use antimatter for both kinds of searches. Direct searches mean that you try to somehow sense the dark matter that's around you, and indirect is like in fifth forces, for example, is an indirect manifestation of the same underlying particle, but in different ways, not necessarily dark matter. EDMs, we'll hear more about EDMs in Tanya's talk later. Precision spectroscopy, nuclear magnetic resonance, astrophysics, and accelerator-based searches. And I was going to sort these kind of searches between direct and indirect, and then I realized that each one of these is currently being used in both ways, as direct and indirect search. So in US currently there is an ongoing process called Snowmast, is where the physics community broadly decides what they want to do in the next years. And I'm very pleased to see a number of papers dedicated to dark matter searches, and even specifically to the ultralight bosonic dark matter searches. And of course, anything we do in experiment has to do with experimental techniques, and there's a paper on quantum sensors for precision measurements. Now, we had a special issue last year on quantum technologies for discovery in fundamental physics that was co-edited by Mariana Safronova and myself, and we wrote a little editorial, and I'm showing you this because I'm very, very proud of this paper, because it's the only time in my career when the paper was rejected from the archive. I think maybe the title had to do something to do with it. Okay, so now what I would like to do, the time is ticking, right? So now what I would like to do is to give you a small sampling of how we go about looking for these types of dark matter. And this is by no means a comprehensive survey. So I just basically included some of the things I myself am interested in and involved in it to some degree. For example, we look for dark matter using nuclear magnetic resonance, and this is the Casper experiment. The Casper experiment is delocalized. It has one headquarters at Boston University, led by Alexander Sushkov, and another at Mainz. And we look at slightly different couplings of dark matter, but the general idea is that you prepare a nuclear polarized sample, and you know, an NMR, in order, okay, and this is in a leading magnetic field, and in NMR, in order to flip the spins, you apply an oscillating transverse field, and when this oscillation frequency is at the Larmor frequency, the spins start to go off the axis and spin like this, and this can be detected. This is the usual NMR. So the idea of these experiments is that we replace this transverse oscillating field with dark matter. It does the job for us, and then we scan the magnetic field and look for resonances. Turns out to be a sensitive way to search for dark matter. Now, there are other ways. So recently, there are these nuclear spin masers and spin amplifiers that have been introduced. And here I'm showing an experiment at the University of Science and Technology in China. And this is also a quite sensitive dark matter search at in the low frequency range with xenon. And now this is a direct search for dark matter, which this is a magnetic shield here. And of course, the dark matter field ignores the shield and goes right in. And we can, sorry? Yeah, naturally. And but you can do also indirect searches. For instance, these dark matter particles, they can induce an exotic interaction of the spins with the mass. And so we have here a helicopter looking like device where a mass is moving around outside the magnetic shield, and we're looking at a synchronized spin precession inside there. Now, this bosonic dark matter can come in a variety of flavors, so to say, and one of them is so-called topological dark matter, where it's some kind of a concentrated object, either something that's called a boson star or axion domain wall. And one of ways to search for these things is a network of sensors, and we have this Snowmast experiment, which is looking for axion domain walls. Now, after the GNOME, there were other networks introduced that use atomic clocks, and they look for similar kind of physics, but through a different manifestation. So the point is that the pseudoscalar particles, they talk to spins, and scalar particles, they mimic variation of fundamental constants. Then you may have seen Nathaniel. He's here in the audience, and Nathaniel has championed this interesting search. So there exists weakly interacting or non-interacting matter that still interacts gravitationally. It is possible that somehow it got trapped in the gravitational field of the Earth, and if it so happened, then it will be sloshing around potentially, and there is a network of sensitive gravimeters. These are amazing devices that can measure the small g with 10 to minus 12 precision in 1 second of measurement. And you can actually download the data from 40 years of operation of these devices and analyze it. And so we analyze it for specific frequencies and look for dark matter this way. Now, scalar dark matter, like I mentioned several times, effectively changes the values of fundamental constants. So if you have, let's say, an atomic energy level, then it should be moving around with the frequency given by the mass of the field. And then if you have, let's say, a cavity, optical cavity, then its lengths also should be changing, but the dependencies are slightly different, and the cavities also are not sensitive to fast variation. So basically, by locking a laser to a cavity and then observing the frequency of an atomic or molecular transition, you can actually look for manifestations of dark matter, and it's quite easy to go to the level of 10 to minus 18. And in contrast to atomic clock, where 10 to minus 18 is hard work, this is very easy for such a setup. Then I would like to mention something that's particularly dear to my heart, and this is an idea of Stefan Ulmer. So this is the base experiment where these guys are studying single or pairs of antiprotons, keep them inside for months, and do exquisitely precision measurements. So the idea was to analyze this for the interaction with pseudoscalar fields. And if you take this experiment, as a equal weight counterpart of normal matter experiments, it's not super sensitive. However, this is like the first constraint of interaction of dark matter with antimatter. And there is a possibility, and which is not the lunacy, which is a very, I would say, good possibility, that dark matter interacts very differently with antimatter as opposed to with normal matter. So this is a very interesting experiment. And now we have an ongoing project also where we use levitated magnets for looking, yeah, eventually for exotic interactions. Now, these exotic particles that you had used to explain dark matter, they can also lead to fused forces. I say this 10th time, 10th time in this talk already. And it was pointed out perhaps for the first time by Moody and Wilczek, which made a small catalog of these interactions. That was later revised and expanded by Dobresko and Moschow, but this was also not quite complete. And the latest catalog is the result of heroic effort of a number of people, and two of them, Pavel is around here, I hope. Yeah, there he is. And also Philip Ficek from Krakow, who got into this by coming to me as a summer student and then continuing. And also some more senior people. And this gentleman here is Lei Zong. It's not Victor Flambaum, I assure you, but he is now leading an effort of actually now taking this theoretical catalog of possibilities and now matching it to what has been done in all experiments. So we hope to provide a nice review and a guide for what can be done. Okay, now how many minutes do I have? Huh? Okay, so I have like 7 minutes. Okay, good, super. Okay, I gave you some very general remarks. Now I think that maybe one experiment I should explain in a bit more detail. And this just appeared, I think, yesterday or several days ago on the archive. And this is one of the series of experiments spearheaded by Min Jiang. He's from the group of Professor Xinhua Peng, and he spent some time with me first at Berkeley, then at Mainz, and now he's a junior faculty member there and extremely energetic and active setting up these kinds of experiments. And this particular one is a search for a fused force that has an interesting property. It's peri-violating. And one of the entries from this catalog of the exotic interactions you can see here. So what you see here is basically a derivative of the Yukawa potential, and then it's multiplied by the cross products of the spins of interacting particles, for example, neutron and electron here, and the radius vector connecting these particles. Now, let's look at the what happens when we do spatial inversion. So we have two spins, so the product doesn't change, and we have RA changes. So this is P odd, and similarly, you can see that it's a T even effect, P odd and T even effect. And what happens here is if you imagine that you have a spin source, and in our case, it's a source of polarized rubidium atoms, then it creates a pseudo-magnetic field over here, and it's directed in this direction as shown, and then the spins of the probe, spin sensor, and in this case it's again this nuclear spins of xenon and the spin amplifier. They will be processing in the presence of this field, and you can see that you have quite a different situation if you look in the mirror. And in fact, this picture also suggests experimental reversals that you can use to distinguish this real effect from systematics. This is how it looks. Here is the spin source, and here is the spin amplifier, and this is its sensitivity as shown as a function of frequency. So you see it's a resonance search, and you modulate your spin polarization at the frequency where your spin amplifier is most sensitive, and then you look for the signal. And so the results of these experiments are shown here. So we are probably here the force range from very, very long, means very, very light mediator, to short ones to about a centimeter type of scale. And there was earlier work of Larry Hunter, who used the polarization of the Earth as a source of exotic field, or magnetized Earth, and did some measurements there. And the other thing you can see here is our own experiment on measurement of parity violation, actually isotopic dependence of parity violation in terbium atoms several years ago at Mainz. And for this particular kind of interaction, Sapphire is doing much better and projected to do even better in the future. All right, and so this is the electron neutron, and this is proton neutron coupling. All right, since I have only 2 minutes, I will be extremely quick. I just want to say that there is a very, very exciting idea, and I've been very lucky to spend a significant portion of my time in the last few years working on the physics case for what can be done with this thing. And it's, in one word, turning the LHC in a tabletop experiment, at least in spirit. So the idea is that you have highly charged ions, non-bare ions. So typically this would be something like hydrogen like lead or something like that. And the relativistic factor for these things is up to 3,000. And if you just shine a normal laser heads on with the ion, you can tune to the large energy in the ion frame and do resonance spectroscopy. Moreover, scattered light goes in a narrow angle 1/gamma in the direction of the propagation of the ions, and you can do lots of interesting stuff with already with the primary beams, but also secondary beams, and then even tertiary beams, but things you produce by bombarding the targets with electrons. Right, so in the remaining half a minute, I would like to mention something. So it goes with the story. I have a dear colleague with whom I've been collaborating for many years. This is Professor Mark Ryzen at the University of Texas at Austin. And in 2008, Mark invited me to give a talk at Austin. I came there, Mark arranged for dinner, and he invited Steven Weinberg, the great Steven Weinberg of the Standard Model, because Mark and Steve were very close and talked physics a lot. And so one of the last problems that Steve was working on before he passed away, in fact, he published a paper in 2016, was some kind of a generalization of quantum mechanics. Don't have time to go into what it is, but the prediction that he made is that if you have 3 atomic clocks, 1, 2, and 3, and then you try to see whether 1 plus 2 is equal to 3, you may not, in fact, see that in his generalization of quantum mechanics that this is the case. And then somehow they couldn't find a good system. So Mark somehow called me up recently to try to revive this thinking about this, and we immediately realized that in fact such an experiment has been done already by Andrew Yaich in radium ions, and that beautiful possibilities exist in the terbium. Then we talked to people and calcium plus. This has been done already. Anyway, I just want to advertise this, that this is something I wouldn't make a career after checking if 1 plus 2 is equal to 3. But if you do have such a close system, please check. And I think people in this audience can probably do it at pretty high precision. This the paper is on the archive if you're interested. Yes, and we already, by the way, heard about HD test in an earlier talk, okay, in this very conference. All right, so I'm out of time. What did we talk about? We talked about elephants, of course, and maybe there's only one elephant and not many. And there are many ways to hunt these elephants, which makes life interesting, I think. And then I told you a little bit about the parity violating fifth force search based at the University of Science and Technology in Hefei. And then I mentioned this Weinberg's generalization of quantum mechanics, the 1 + 2 = 3 idea. And I thank you very much for your attention.
Thanks very much for the great overview talk, Dima. Questions for Dima? Okay, let's start here.
I would like to ask a question about this NMR, nuclear magnetic resonance. So you gave very many examples. I just wonder how this nuclear magnetic resonance can feel the dark particle. Would they be then absorbed by the nucleus?
No, and so there are different ways. So these are pseudo scalar particles, and one way is this axion, a pseudo scalar particle, was introduced to explain why the CP violating angle is small. So this field actually generates the electric dipole moment, and if there is an oscillation of the field around us, the dipole moment will be oscillating. So you have then, and Tanya will talk about this also, about the static and oscillating EDM. But if you put an oscillating EDM in a static field, then this D dot E interaction, right, will do the same thing as mu dot B, which is the magnetic field. So the one way, another way is it turns out that there is a so-called gradient coupling. So you have the pseudoscalar field, and if you take the gradient, this looks in terms of symmetry is just like a magnetic field. So then it's just mu dot B again.
So thanks for the talk. I was just wondering, so there was this idea that you showed for locking the cavity to a laser and then checking the precision on a atomic transition. So what is this uncertainty of 10 minus 18? 10 to minus
It's delta
18?
nu over nu currently. So these experiments have recently been done with atoms, with cesium, and also with molecules, I2 molecules, and the precision is pushing towards 10 to minus delta nu over nu to 10 to minus 18.
Okay, and then what you look for is any difference in the energy shift?
Okay, so yes, so an optical cavity, if let's say alpha is changing, for example, right, the fine structure constant, then the Bohr radius is changing, and the cavity should be moving, expanding and contracting together with the change of alpha. But if it happens fast, the cavity cannot follow. It just basically locally deforms, but it cannot follow as a whole. And if you lock the laser to such a cavity, good, then you have a stable reference. But atoms don't have such inertia as a cavity, and the energies will be moving like this. So then you just basically, we have, we're going fancy. We have not just saturation spectroscopy, we have polarization spectroscopy. So we see that the large slope, and for example, right, we do different things for different cases. And that very simple thing already gives you this kind of sensitivity.
There's another question. Last one in the interest of time.
Yes, thanks for the talk. So in what scale then would dark matter interact with antimatter? So basically, would you see then in the transition of antimatter the same kind of effect that you're saying more in antimatter than in normal matter?
Yeah, it's possible. So it is possible that the interactions, depending on the fields and so on, but there are models where there are different interactions, and you would then see, for example, the effect in the base experiment and not in all others. Yeah, well, let's talk at coffee. I don't think so. I'll give you an example of a 100% asymmetric. This has to do with the anti-quark nuggets that I would love to tell you about anyways, and they interact completely differently with matter, and antimatter, and there is no monkey business there.